Well, we've made it. It's our last lecture. And I thought this would be a good time to summarize what we've done. And a good place to start is Maxwell's equations. There were a number of disjointed theories: Gauss's law, Faraday's law, Ampere's law. Maxwell tied them together and said these all relate to the same thing. And he expanded on them, and he even did the mathematical derivation and came up with the speed of light. We'll talk about that shortly. But let's take a look at what these laws tell us. Gauss's law tells us that charged particles create electric fields. Gauss's law for magnetism tells us that there are no magnetic monopoles. Faraday's law tells us that a changing magnetic field creates an electric field. And the Ampere Maxwell Law, the first part, that's the Ampere's law part, tells us that current creates magnetic fields. And the second part that Maxwell added to make this equation correct tells us that changing electric fields create magnetic fields. So this is almost all of what we did this quarter in electricity and magnetism, but we're missing something. What are we missing? We're missing forces, right? We talked a lot about forces between electric charges and between charges moving in magnetic fields. We need the Lorentz force law. And that's pretty much our quarter in a one-page summary, isn't it? Electricity and magnetism can be summed up right here. Let's see how that fits into the bigger picture of classical physics. In mechanics, we learned about motion, Newton's laws, and gravity. This is our Physics 4A class at Foothill College. In our electricity and magnetism class, we just talked about the main equations. I'll rewrite them here. And in our thermodynamics class, that's Physics 4C here at Foothill College, you learn the laws of thermodynamics. Some people say these 11 laws are the foundation of classical physics. That physics works in our everyday lives, as we've seen in the last couple of quarters. But if you start to look what happens inside of atoms and in other extreme situations, these laws break down. And we need modern physics for that. At our campus, that's Physics 4D. Let's talk about electromagnetic waves. In a wave, we know that something is oscillating, something is vibrating. In a sound wave, for example, a disturbance is created. Maybe our vocal cords create a pressure disturbance in the air molecules. And that pressure disturbance, the air molecules vibrate a little bit, and that disturbance propagates through the air molecules. And eventually, when it gets to our eardrum, we perceive that as sound. This disturbance propagates through the medium. Sound needs a medium to travel through. Gas, liquid, or solid, it needs a medium to travel through. In an electromagnetic wave, what's oscillating is the energy back and forth between the electric field and the magnetic field. And this does not need a medium to travel through. Electromagnetic waves can travel through a vacuum. As the electric field changes, it creates a magnetic field perpendicular to it. And so the electric field is oscillating in one plane, the magnetic field is oscillating in another plane, and the wave propagates perpendicular to those two directions, as we see in this image here. I was going to attempt to draw it for you, but I think you've figured out by now my drawing skills are somewhat limited, so I took this from the textbook. The electric field is oscillating in one direction, the magnetic field in another direction, perpendicular to it, and the wave is moving, is propagating perpendicular to both of those directions. In this case, our wave is propagating to the right. One of Maxwell's biggest contributions here was that he did the analysis, and he determined that if the electromagnetic wave was moving too slowly, it would have to be losing energy. And if it was propagating through a vacuum, where would that energy be going? He also saw that if it was going too fast, if it was moving too fast, it would need more energy. We'd have to add energy to it. Well, where is that energy coming from if it's propagating through a vacuum? So he surmised that these waves, electromagnetic waves, had to move at one particular speed, the only speed they could move at where energy was conserved. They weren't losing energy, they weren't gaining energy. And he did the mathematical derivation and calculated that speed. That is the speed of light. Let's take a look back at Maxwell's equations. And we see these epsilon naughts that show up in our electrostatics equations and the mu naught that showed up in our magnetic equations. And here, Maxwell's contribution to the Ampere Maxwell Law has epsilon naught times mu naught. It turns out that 1 over epsilon naught times mu naught, the square root of that, is this special speed that the waves have to propagate at in order for energy to be conserved. That's the velocity of an electromagnetic wave. That turns out to be 3 times 10 to the 8th meters per second. We have a special symbol for that. We call it c, the speed of light. Electromagnetic waves are just the general case of light. Light is the special case because we happen to be able to see it. Our eyes are tuned to the frequency of visible light. But there's nothing different about a light wave as a radio wave or an X-ray. They are all the same stuff. They're all electromagnetic waves. Let's take a look at the complete electromagnetic spectrum. Again, all of these things are the same stuff. Electromagnetic waves. We give special names to certain regions because of the way we use them, but there's nothing really special about one over the other. It's all the same stuff. At the very low energy end of the spectrum are radio waves and microwaves. Radio waves and microwaves, those are very low energy. As we move up to higher energy, we eventually get to our infrared and then our visible light. And if we go beyond that, we get to ultraviolet and X-rays and gamma rays. If we take a closer look at this section right here, the visible part of the spectrum, we see this. The visible light itself is made up of different colors. Red is the lowest energy of the visible light. It's just above infrared. And violet is the highest energy of the visible light. That's just before ultraviolet. Now, everything emits electromagnetic waves. Well, everything that's above absolute zero. As you warm something up, it emits radiation. It emits electromagnetic energy. Something that's really, really cold might emit radio waves or microwaves. As it warms up a little bit, it emits higher energy electromagnetic radiation. You and I emit in the infrared part of the spectrum. Our eyes aren't tuned to that. Our eyes can't see that. But maybe you've seen in the movies, the military has those night vision goggles that can see in the infrared part of the spectrum. And there are animals that are nocturnal that have eyes that are tuned to the infrared part of the spectrum. But our eyes are tuned to the visible part of the spectrum. As you heat something up a little bit more, it goes from infrared, glowing, giving off infrared radiation, to starting to glow red hot. When you heat something up, it eventually glows red hot. It's giving off red light. That's the lowest energy visible light. And if you keep heating it up, pretty soon it gives off all the colors of visible light. So all the colors of visible light together make white light, so it glows white hot. And if you could heat it up some more, it would eventually glow in the blue and violet part of the spectrum. And if you could heat it up some more, it would be giving off mostly ultraviolet radiation, and then X-rays, and then gamma rays. And if you look at the stars at night, you'll notice some of them look white, like our star, like the sun. They're about the same temperature. That star you're seeing and our star, the sun, are about the same temperature if they both look white. Some stars look red. They're cooler than our star. They're cooler than the sun, and they glow more in the red part of the spectrum. And some stars look blue. They are hotter than our star. They're hotter than the sun. They glow more in the blue, ultraviolet part of the spectrum, and they give off higher energy electromagnetic radiation.